就是有凝聚力的感觉。对啊，就天文是没有天文台很奇怪，有那种感觉。别的一个天文台，
大家会起，学生会起问，
而且是一个很好的宣传机。
哦，对啊，对啊，对啊。
像最近我们就是在这边，像还有就是把它弄得比较好，也修了一些东西宣传。对对对，然后就很多宣传，
有人很热心在弄。
对啊，有什么天文的活动就可以去，就增加了。我不知道你们一个，其实广大的群众都对天文蛮有兴趣。是，让大家认真看新闻。是啊，那也没关系，先对不懂天文有好感的，对啊，
大家先来看星星，
所以我就要先去学习看星星。哎，对啊，你会吗？我会，我以前有参加过什么天文课？不会啊，我从来没有啊。那你既然会讲，对啊，我以前大学是天文社，但是我对望远镜一起学。我以前
我也不喜欢那个 part，
我完全不喜欢，
就觉得好像
到仪器我就
请调好给我看。
对对，觉得
我又超白目的，以前我申请 IA 的时候，就是那种我也好看到有资料他把如果是那种他就自己把我找进来，然后我也不知道他什么方式，我开始我就要跟他说，我其实对看戏剧非常有兴趣。
还好吧。
他应该会很伤心吧？
我觉得
他要这句话不会心碎吗？
不会啊，我也不会。
应该也是会说很生气。
他最喜欢劝退人念天文，他说那你不要来。
没有啊，没有这样讲，他就只是对我好奇，然后
结果你们没
有啊，都别人做。
对，所以就没办法。就可以带了。
哦，
他只是好奇。他是问他不知道。
可以请会看的学生教你。
对啊，
我觉得会看的
哦，对，
会看。
对，哎，你们有天文社？
就是要跟我在一起。
对，我跟你讲，先成立了天文社就会有学生，然后就会有很厉害的人，
对，就会有人来。
对，所以我就是想说要培养小学生是可以玩的，
就是要成立天文社。对，只要有天文社就会有人。
然后给他们有一个地方可以聚集在一起，
对，有一个社办，
人一直在那里就会起来。
所以我就要做很多研究。
倒是，我也觉得他就没有你的工作好杂哦，杂到研究大概只有小点时间剩下，而且又切的那样碎。
不过我最近还有就这个是跟我说我借口，就我这2年就有一些东西，我就要
哦，就在做
对人借口，所以才会这样。
的确，其他事情比较有趣。我觉得就是有些弄学生的事情，
你们有什么要弄学生的 duty 吗？
就是那个什么导生，
导线，
就跟他们聊天啊，吃东西啊。对，还有就是 mentor， pro mini。
我去年当了一个就是现在那个
缠上的，缠上你是什么意思？他动不动就来，
对，他就动不动找我来我家里吃，然后说我吃饭，然后晚上还说
是男生，
就很有意思。就我没有办法判断，因为他真的很奇怪，就是他好像也会对其他老师但是就是又对我很奇怪，所以我就有点然后后来才我就说换掉，
好生气哦！那他还有在出现吗？
就后来就没事，然后就
换人就好了，那就换成年那个。
也要看好不好演，不是每个系的老师，不见得那么敢演。
好有趣哦！
对啊，应该很困扰。
对啊，
他说很困扰，真的超级困扰的。
你跟老师都这么亲密哦？
也没有很亲密，
我还没跟他们吃过饭。
跟他们聊天。我不知道你们学校是这样吗？就是我们学校是他们修课必须要跟导师要求，
我们没有才能。所以其实是会有一些互动。
对，就是他至少要来跟你要求，然后就会借机见面一次。
OK。
哦，就你一个人对一个人，所以你们班导，
是2人一组。 学。
听说大家都是只想吃饭。
对啊，就是请客就好了。
有些人是连饭都不敢吃。
真的。
对啊。
现在的学生你都没有办法用饭吃。
不是很厉害的饭。
这跟我理解就是学生不一样。
因为钱不够，还是你有比较好吗？
不是说都请假排。对啊，我就说相反从右。就因为他不是有辅助吗？有导师都要这样。然后那个有学生超乖，然后他就来吃饭，然后就点了很多，就吃得下都点，然后他就点了一大堆，就说老师怎么样吃饭。然后
他就这样讲吗？
对，然后结果他进来之后怎样？他就吃一次，然后你还留了一下带回家搞宵夜，再来一次力量。哇，对，好会赚。
要是我一定挑吃到饱的餐。其实我觉得学生就是吃到饱。
对，是，而且跟年轻人吃到饱，
他们真的会吃到饱。
因为自己都已经
而且同年龄就是去那种店，大家都
没有，就是早就没有在做吃到饱这件事情。
对
啊，然后大家都说啥嘞？
办公室在，
你就在中2，就是它有一个桥过去，就是
可以接过去。
对。然后我们在5楼。
你有没有来过？去年讲过。
对啊，我记得没有在之前的
没有很熟，就蛮近的，
就是隔壁栋。
像这栋建筑也很复杂。
对，我每一次跨过桥来到这边，我就已经
是这栋复杂吗？
对，我觉得就是这边的另外一个在天气，因为我们在天气之后，我觉得那边我们跟我其实已经换班了，他10月才开始
P， 原来是 P， 我就觉得我到底在走什么？
台湾然后那里前 P 的那个角落，我就有一个柜台，然后每次进来这边之后，我就觉得好小，我在没有进化到我的那种，
所以不是我的问题，是它本身就是一个，
我觉得它就是 layout 的清楚。
每次来这边都是在看。
我对现在就是除了我停车到我的系馆以外，住的地方还有小吃部。
我在是在公司那么小，我去1整年都是没有从后门走出去。
对，用不到。
我也是，来吃哪一个点心？我也要去那个喝看一眼。还有吗？
All right, I guess we can get started. I'll be the coordinator for the session, and we got 2 talks for this session from junior fellows. It's encouraging. And the first talk will be provided by Ting-Wen from UC Santa Cruz. We'll be talking about feedback signatures and CGA. Please.
Hello, can you hear me? Is it too loud or is it okay? Right? My voice is too loud. Okay, so hello everyone, my name is Ting-Wen. I'm at UC Santa Cruz as a postdoc fellow. And first of all, it's my great pleasure to be here. I would like to thank the organizers for giving me this opportunity to present my study. And in addition, for organizing this really very good, interesting conference, I'm really enjoying the discussion and talks. So in the following, I'm going to talk about stuff outside of galaxies. So in the past 2 days, we have learned a lot about the connection of supermassive black holes and the galaxies, and focusing mainly on the galaxy properties. And now in the following, I'm going to talk about gas outside of galaxies and what can we learn the feedback mechanisms through the properties of gas around galaxies. And most of my work is done in collaboration with these four gentlemen, Masataka Fukuhita at University of Tokyo, Chris Bernard at Johns Hopkins University, Audrey Moore at UMass Amherst, and Guangwen Zhu at Johns Hopkins University. So as we learned from this conference, we now believe that gas flow processes play a crucial role in driving galaxy evolution. Galaxies are expected to accrete fresh gas from the interstellar medium, intergalactic medium, to supply the star formation activity. Meanwhile, galaxies return metal-rich gas back into their surroundings via feedback mechanisms, which is the topic of this conference, driven by the explosions of stars and or the activity of supermassive black holes. And these gas flow processes regulate the amount of gas in and out of galaxies, at the same time shape the properties of galaxies. At the same time, these gas flow processes leave their signatures in the gas around galaxies, the region, now we call it the circumgalactic medium. So circum means around, so it's the material. Around galaxies, roughly speaking, those are gas bound within the visual radius of dark matter halos. And if we can study the properties of circumgalactic medium and their relationship with its relationships with the properties of galaxies, we will have a better understanding of how these gas flow processes, especially feedback, influence the evolution of galaxies. And I just want to mention or emphasize the importance of studying the circumgalactic medium, because all the feedback mechanisms that we discussed, they all require the interaction or the energy exchange between the galaxy and the circumgalactic medium. Okay, so by studying the CGM, we can try to understand the feedback mechanisms. And one powerful technique to probe the CGM is called absorptionized spectroscopy. The basic idea is that if there is a bright background object, most of the time we use a quasar, and its line of sight intercepts the gas of a foreground galaxy, then the gas will imprint absorption-like features in the spectrum of a background object. Those absorption lines are due to quantum transition of different metal elements or hydrogen as well. And by detecting and characterizing those absorption lines, we can extract the properties of the circumgalactic medium and study its connection with galaxies and try to understand how feedback, what's the role that feedback played in changing the properties of circumgalactic medium. Okay, and in this talk, I'm going to focus on studying the circumgalactic medium using this absorptionized spectroscopy method. So what would be the signatures of feedback in the circumgalactic medium? There are three possible scenarios, or there are three possible signatures. The first one is that if there is star formation feedback impacting the circumgalactic medium, we will expect that there's a correlation between the properties of the circumgalactic medium and the star formation activity of galaxies. And that will be the first signature of feedback in the circumgalactic medium. Second, if there are feedback mechanisms for galactic outflows driven by feedbacks escaping from galaxies, we expect that the gas tend to escape the galaxies along the minor axis of galaxies due to the fact that in this direction there are less pressure from the interstellar medium. So the gas tend to escape the galaxies in the direction with less pressure. So if we measure the spatial distribution of CGN, then the signature of feedback will be the anisotropic distribution of the circumgalactic medium. And this would be the second signature of feedback in the circumgalactic medium. And finally, we know that the galactic outflows driven by feedback will bring gas from the interstellar medium back into the circumgalactic medium. And we know that the metals form in stars in galaxies. And those feedback mechanisms, those outflows will bring metals from the ISM into the circumgalactic medium and enrich the metallicity or the metal content of the circumgalactic medium. So the metallicity or the metal enrichment of the CGN will be the third signature of feedback in the circumgalactic medium. So in this talk, I'm going to show you that by using data from large surveys, especially the Sloan Digital Sky Survey, whether or not we can try to probe these three signatures of feedback in the circumgalactic medium to see that whether or not observationally, we really detect those signatures of feedback in the CG. Okay, any question, please?
What's the typical density for circumgalactic medium?
A wide range. So in fact, the CG has different phases, and different phases have different densities. The hot gas phase could be 10 to the minus 4, 10 to the minus 5 per cc. You mean the density, right?
Yes.
10 to the minus, yeah, so the hot phase can be 10 to the 5 or 10 to the 4. And the cool phase that I will talk about can be like 0.1 per cc. So they coexist with each other around galaxies.
So is there any observational signature for this inflows, or is it just a conjecture inflows?
Yes, there are some. Actually, it turns out that it's very difficult to detect the inflows observationally. One possible signature that people find is actually if you look the galaxy down the barrel and use it as a background, occasionally you will see a redshifted absorption, indicating that the gas is actually moving toward the galaxies. And from our Milky Way, if you look at the high velocity clouds, actually some of it is moving toward the galaxies. That could be the signature of inflow. But the question in that scenario is that we don't know the distance of gas. And from the line of sight study, it's very hard to distinguish outflows or inflows from the velocity information because there's a degeneracy between whether it's moving over here or it's actually moving out in this direction. Okay? So in following, I'm going to use data from Sloan to show you that whether or not we can explore these three signatures of CG and figure feedback in the circumgalactic medium. So to start with, Sloan until today has observed more than 500,000 quasar spectra that we can use as a background light to probe the absorption light features due to the intervening circumgalactic medium. So my collaborator Ju and Brisbane several years ago have developed automatic algorithms to detect those absorption light features observed in small quasar spectrum. Here's just an illustration. In black is an observed quasar spectrum from Sloan, and in red they use a machine learning method called non-negative matrix factorization to model the SED of the quasar and remove the features intrinsic to the quasars and obtain a normalized spectrum from which absorption due to the circumgalactic medium. As you can see, there are some absorption lines. Okay, and then they can run detection algorithms to detect those absorption lines from this normalized spectrum. And they apply this algorithm to all the Sloan quasar spectra and compile a large, even until today, the largest absorption line catalog consisting of almost 100,000 systems from redshift 0.4 to 2.5. Here's just a visualization of the catalog. Now for each row, it's showing the absorption spectrum, the intensity of the absorption spectrum, ordered in absorber redshift in observed wavelength. And the dark region indicates absorption line features. And as you can see in the middle, there's a strong absorption line feature, which is actually due to two absorption lines. It's a magnesium 2 doublet. And the reason they target the magnesium 2 doublet is because it's a doublet feature, it's strong, so they are easy to be detected from low signal to noise Sloan quasar spectrum. And in my talk, I will going to focus on the CG and trace by the magnesium 2 absorption lines with those gas tend to have gas about 10 to 4 Kelvin. So it's a cool phase of the circumgalactic medium. And in addition to magnesium 2, you can see other metal absorption lines. Those are iron 2, aluminum 2, or aluminum 3, or carbon 4, silicon 4, etc., etc. Those are all coming along with the magnesium 2. Okay, but in my talk, I'm going to focus on the gas traced by magnesium 2 absorption lines. And having this large data set, now we can start to address these three signatures of feedback in the circumgalactic medium. So first of all, we want to prove the correlations between the properties of galaxies and the circumgalactic medium. And we can make use of this large data set by performing a cross-correlation method by correlating those absorption lines with photometric galaxies detected in imaging surveys like the Sloan Digital Sky surveys, like the Dasilex imaging surveys. And by performing such cross-correlation measurements, we can directly extract the signatures, extract the information of galaxies associated with those absorption lines without using any information of the galaxies, which allow us to largely increase the sample size and really explore how the properties of CGN correlate with the properties of galaxies. So in practice, maybe I would skip the detail of this methodology due to the time constraint, but if you have questions, you can ask me later. Okay, so this is about the method. I will skip, but basically we can use this cross-correlation method to extract the properties, connect to those absorption lines, and study the relationship between the two. And I'm just going to summarize the main results. Okay. So here is the main results. Now the y-axis, I'm showing the covering fraction, which is the probability that you can detect those absorption lines at a given impact parameter from galaxies as a function of impact parameter. And the color indicates that the covering fraction around star-forming galaxies and around passive galaxies in red. And we found that within small impact parameter, the covering fraction around star-forming galaxies is several times higher than the covering fraction around passive galaxies. It's almost 10 times higher, indicating that there is correlation between the gas distribution and the star formation activity of galaxies. Okay? And at a larger scale, we found that the covering fractions become consistent with each other at a larger scale, following about -1 slope, and suggesting that at a larger scale, the gas tend to follow the matter distribution. But within smaller scale, there's a correlation between the gas distribution and the star formation activity. And this could be the signature of feedback. Okay? And as I mentioned, we can perform these cross-correlation measurements with different data sets. And the density image series allow us to probe this distribution as a function of redshift, which is shown in this plot. Now, again, the y-axis is the covering fraction as a function of impact parameter. Now I changed the unit a little bit. Now it's not physical, it's the ratio between impact parameter and the virial radius of the dominant halo obtained by the halo mass inferred from stellar mass of galaxies. And this is a covering fraction around star-forming galaxies as a function of redshift. And what we found is that the covering fraction of gas around star-forming galaxies increases with the redshift, which is similar to the evolution of the star formation rate in galaxies, as TC mentioned earlier today. Okay, so this suggests that the gas distribution evolves similarly with the star formation activity through cosmic time. And this could be the signature of feedback in the circumgalactic medium. And this is for the gas distribution. But you might wonder, how about the gas kinematics? Can we also see some signature of gas kinematics? Some signature of feedback in the gas kinematics around galaxies. In order to do so, we need to have precise redshift of galaxies. And my previous method, I skipped, is actually just using, sorry, let me rephrase again. In my previous method I used to obtain this information, we don't have precise redshift of the galaxies. But Sloan also provides a nice data set for us to probe the gas kinematics around galaxies. Last year, Sloan just finished the survey for emission line galaxies with about 200,000 systems at redshift 0.8. And this is just an emission line spectrum. Sorry, the composite spectrum of the emission line galaxies from Sloan, and you can see those emission lines, indicating that are star-forming galaxies. And from this spectra of emission line galaxies, we can obtain the precise redshift of galaxies and try to measure the gas kinematics around those emission line galaxies as a tracer of star-forming galaxies. This is just another visualization of the data set for each row. It's showing the galaxy flux as a function of galaxy redshift in observed wavelength, and you can see those emission lines. Okay. In addition to those emission line galaxies, we can also use the luminous ray galaxies obtained from Sloan as a tracer of passive galaxies. And Sloan, until today, has obtained 1 million luminous ray galaxies around redshift 0.5. And this, again, is just a visualization of a data set. For each row is indicating the galaxy spectra as a function of galaxy redshift in observed wavelength. And you can see the 4,000 break evolve as a function of redshift. And having these two data sets, now we can measure the gas kinematics, the CGN gas kinematics around these two galaxy populations. Okay, so to do so, I start from the galaxies and I stack the background quasar spectrum as a function of impact parameter to obtain the average absorptions around those two populations as well as the gas kinematics. Okay? And here is just an example of the composite spectrum, the background quasar composite spectrum. And you can, as a function of impact parameter from 20 kiloparsec to 1 megaparsec. And you can see the magnesium to absorption lines from small impact parameter to large impact parameter. Okay, so a large impact parameter, the absorption strength the detection over layer is like 2 to 3 sigma. I want to draw your attention to the y-axis scale. Now at small impact parameter, the absorption line strength is typically 20 to 30% of the continuum, while at a larger scale, it's only 0.1% of the continuum. But because we are stacking a lot of background quasar spectrum, we can actually obtain a very high signal-to-noise composite spectrum and really detect the absorption line at large scale. Okay, and from this absorption line, we can extract the information based on the line width, which contains the gas kinematics information. Any questions? Okay, so
does the relative strength of these two lines give you any information? Because they actually change.
That's a very good question. So in fact, yes and no. So in most of cases, those lines are saturated. So actually, it's very hard to use the line ratio. So in principle, if it's not saturated, it's 1 to 2. So this line, the line on the left should be twice stronger than the one on the right. Okay, but here you see it's almost comparable to each other, suggesting they're actually saturated. Okay, so now I'm showing the gas kinematics, the line of sight gas velocity dispersion around emission line galaxies and around luminous-ray galaxies as a function of impact parameter. And we found that the gas, the velocity dispersion, is about 100 km per second around emission line galaxies, while the velocity is about 170 km per second around luminous-ray galaxies. But we need to be careful if we want to compare the effect of the central galaxies, not the effect of the gravitational potential, then we need to remove the effect of gravitational potential. And we know that these two galaxy populations tend to live in halos with totally different halo masses. The emission line galaxies tend to live in halos with 10 to the 12 solar mass halo, and while the luminous ray galaxies tend to live in halos with about 10 to the 13.5 solar mass halo. So they have totally different gravitational potential, and we need to remove this feature, this effect out. So here I'm showing the y-axis now is the gas velocity dispersion divided by the dark matter particle velocity dispersion, which can be used as a proxy, or which can be used as a proxy of the gravitational potential. Okay. And as you can see, once we normalize such gravitational effect from the dark matter, the velocity or the gas velocity around emission line galaxies actually moves similarly with the dark matter particles, while the gas around luminous ray galaxies only move with 50% of the velocity as the dark matter particles. And this suggests that in the gas kinematics, there's also a correlation between the gas kinematics and the star formation activity of galaxies. And this could be the signature of feedback in the CGN. And now we have addressed the first question. I showed you that gas distribution kinematics correlate with star formation activity. And now let's move on to the second signature. As I mentioned previously, that this axis within the small impact parameter can be the signature of feedback. But we need to be careful because we can interpret this correlation in two ways. One is that this axis is actually due to gas ejected from galaxies associated with galactic outflows. And that's why we see the correlation between the star formation activity and the axis absorption of gas. But there's another way to interpret this, is that actually there are some involving gas supplying the star formation activity. Therefore, we see the star formation and the axis of gas around galaxies. But we can distinguish these two scenarios by measuring the as I mentioned, that outflows tend to escape galaxies along the minor axis. So if we can measure the gas distribution as a function of azimuthal angle, and sea level to this axis is actually found along the minor axis, this will be another relative direct evidence suggesting that what we are seeing here is due to galactic outflows driven by feedback mechanisms. And we can do such measurements by using data from Sloan. So we select edge on star-forming galaxies and measure the gas absorption as a function of azimuthal angle. So now here, the y-axis, I'm showing the average gas absorptions, which is similar quantity as the carbon fraction, as a function of impact parameter. And in green, I'm showing the gas absorption along the disk. Okay, and now in purple, I'm showing the gas absorption along the minor axis. And you can see that the gas along the minor axis is a few times stronger than the gas along the major axis, suggesting that the axis absorption around star-forming galaxy we observe is mostly driven by the gas along the pole, indicating that loss absorption is actually due to gas associated with galactic outflows. And this illustrates the second signature of gas feedback in the circumgalactic medium. There is stronger absorption along the minor axis of star-forming galaxies. And finally, we can probe the metal content of circumgalactic medium using the exactly same data set. And as I mentioned previously, that in the algorithm, they target the magnesium to absorptionize because they are strong, so they are easy to be detected from low signal to noise Sloan quasar spectrum. But because they are strong, actually they are saturated, as I mentioned previously, and we lose the information of the column density of metals which are required if we want to extract the column or the metal content of the gas from those absorption lines. But fortunately, we can also make use of the statistical power provided by this large data set. We can combine many spectra together to obtain very high signal-to-noise composite spectra to detect weak unsaturated absorption lines from which we can detect and extract the column density of those metal lines. Here's just one example. Here is a composite spectrum based on 8,000 individual Sloan quasar spectra. And you can see those strong metal absorption lines, again, the magnesium to iron to aluminum carbon 4. And they are all saturated, and the reason they didn't reach to 0 is just because the Sloan spectral resolution is not high enough to resolve such effect. But based on the absorption line strengths, we know they are saturated. And now I'm going to zoom in into very tiny level over here to show the signal to noise of this composite spectrum. In blue, now I'm just zoom in version. Now I'm showing the absorption line strength only about 1% or 2% level, and you can see those weak absorption lines that we can detect from this composite spectrum. And we can characterize those weak absorption lines and extract the column density information and use them to infer the metal content of the circumgalactic medium. Okay? And I will skip this one. Basically, you can use those absorption line information to constrain the metallicity and the gas density to simultaneously by running the cold cloudy simulation. But if you have questions, you can ask me later. And I'm just going to the metallicity part. So using those absorption line information, in addition to hydrogen information based on follow-up observations from literature, that we can constrain the metallicity of the gas producing those absorption line systems. So now the y-axis is showing the metallicity as a function of redshift, and we found that the gas absorption line, the metal absorption line system has metallicity consistent with solar metallicity at redshift around 1, suggesting that they must be originated from galaxies, because this high metallicity is actually comparable to the metallicity of the ISM of galaxies. So it means that the gas must originate from the galaxies and injected by the outflows or feedback mechanisms. And the high redshift, we found the gas, the metallicity of the gas is about 30% solar. And we can also compare the metallicity with another gas tracer called dense systems, which is selected based on the amount of neutral hydrogen column densities. And you can see that they have totally different metallicity, suggesting that they trace different gas in the universe. And one interesting thing is that we found that this redshift evolution is actually similar to the metal evolution of the universe if we use the cumulative stellar mass evolution as a proxy of the production of the metals in the universe. And we found you can see that the evolution is actually quite similar, suggesting that actually the global metal evolution of the universe is reflected in the circumgalactic medium. And this could be the signature of feedback in the circumgalactic medium. So to summarize, by using data from large surveys, especially the Sloan Digital Sky surveys, I've shown you 3 signatures of feedback in the circumgalactic medium. I show you that there's a correlation between the gas distribution and gas kinematics and the star formation activity of galaxies. I show you that the gas around star-forming galaxies can be found along the minor axis, which suggesting that they are associated with gas galactic outflows. And finally, I show you that CGN is metal-rich, and its evolution is in fact following the global metal evolution of the universe. And in the near future, I believe once we have a better understanding of the physics of feedback producing this observed signature of circumgalactic medium, we will have a better understanding of galaxy formation in general. Thank you.
Questions, comments?
Can you combine your metallicity measurements with your spatial distribution measurements and show whether or not the gas is flowing out of different metallicity distribution where you think the gas is flowing in?
I would love to, but I can't in this case. So let's see. So that's the goal people want to do in my study because I'm doing statistical measurements. So from this distribution, I cannot distinguish which galaxy connect to our social lines. So in this case, I'm studying the statistical properties of galaxy connect to also absorbers. But I know that some people start to do that, so they start target individual galaxies and the circumgalactic medium using background quasars, and then they try to measure the metallicity as a function of, for example, the azimuthal angle and as a function of distance. But actually, the results show the mixing properties. So there's no clear evidence showing that along the pole must be metal-rich and along the disk must be metal-poor. And it's actually suggested by the simulation in the sense that simulation has shown that actually a lot of mixing and the metal enrichment, the CGN actually have several cycles of the metal enrichment. So actually those processes will just pollute the average metal content in the CGN in general. So which might be the case that it is very hard, at least for now we are not able to find that along the minor axis it must be metal rich, while along the major must be metal poor.
So for the global metallicity evolution curve, how is it derived? Is it measured within galaxies?
No, so this is just, I use the cumulative stellar mass density as a proxy of the production of metal. So, and the normalization is arbitrary. It's just illustrating the evolution chain.
So, what exactly is this metallicity? Or let me ask a more specific question. If you do this for only iron versus, say, magnesium or something else, you get the same answer?
No. So in this case, actually, I specifically use zinc too. The reason is because we believe that most of the zinc is in the gas phase. While like magnesium to iron, they will be depleted, some of them will be depleted in the dust, which will be a topic of next talk. And CGA is also, those absorbers actually have a lot of dust. Another signature of feedback, because we know that dust must form in galaxies, and we see that in the circumgalactic medium, meaning that they must originate from galaxies ejected by the feedback. But in my case, I only use the zinc as a constraint for the metallicity, just because we think that zinc is, most of zinc is in the gas phase, which is not affected by the depletion, dust depletion.
Last question. Go ahead.
Actually, following the previous question of metallicity evolution, why do you need a arbitrary
That's a good question. I need to think about it. The one problem is actually, I should mention is that in my study I focus on the gas with only one phase. And actually there are a lot of phases that could also have a lot of metal, and they actually interchange the mass at some point. So I'm not sure that based on a single phase of gas, we can estimate how much metals are ejected from the galaxies. In general, I mean, we can estimate how the mass, the metal in this phase ejected from galaxies. That we can estimate. Actually, I have a plot in my paper, but I mean, if you want to consider the total metals ejected from galaxies, then we are not sensitive to that.
Okay, I guess time's up. Let's thank Ting-Wen again. Okay, you ready? You want to get the microphone? All right, next talk will be coming from Huang Yuxiu, our only talk on student. So, no pressure. It's going to be dust evolution and illustrative view simulation, please.
So first, thank you for the opportunity to let me give the talk here. And I'm a master's student from USNTU. And I'm talking about the dust evolution in illustrative view. So let me first address on why we want to study the dust evolution. So first thing is that dust is a subject to any feedback process in galaxy. Like all the processes I will mention later, they are highly environment dependent. So if there are any trend like in gas dynamics in a density field of a galaxy, it will affect our dust formation and evolution. So here I mentioned few, and then also the dust will affect our galactic evolution and then our understanding of galaxies. So these are the few of the effects it can have influence on. The depletion of metal in ISM, catalyst of H2 formation, interaction with starlight, and also heating and cooling in the ISM. And I will show you some examples here. This is a measurement about some galaxies. It shows the metallic depletion from gas phase. That is, some of the metal are captured by the dust, so they are just removed from the gas. So this will change the chemical abundance in the galaxy ISM. Next thing is about the grand catalyst H2 formation. That is, there are mainly three processes that can form a H2. And the grand catalyst is one of the most efficient way to form molecular hydrogen. So if there are any dust in a galaxy, all the process will be dominated by the grand catalyst H2 formation. So it kind of indirectly will affect the star formation in the galaxies. And also that from the previous study by Chen Lixing, she found that actually the formation efficiency of H2 is dependent on the grain size. That is, if your dust population is dominated by small grain, the formation efficiency will be higher. You can form more galaxies like this one, the right one. And if your grain is larger, then you will be less efficient to form H2. And the last thing is about the trend. You will restrict the galaxy as ED. So this is image of Andromeda, the nearby galaxies. So in optical, there are
it seems totally different in optical and infrared. And also from this, so from this purely SED, it's just an illustration that the blue line is the intrinsic SED without any dust. But if there are dust, you will absorb the UV radiation and emit in the IR, so the shape of the SED changes significantly. Then I think this few examples is enough to convince you that dust is very important in galactic evolution. And so what do we want to know? So first thing is the grain size distribution. It's just as I mentioned previously that it can change the HQ formation efficiency. And also it will affect the absorption and the scattering effect in galaxy SED. The second one is the abundance. Like if there are more dust, you will be more likely, the starlight will be absorbed more. And third one is the composition. Then the composition can have several effects, like on chemical evolution or on the, also the galaxy absorption, dust absorption. Sorry. Okay, so I will briefly talk about like there are 5 main factors for dust formation evolution. So first one is stellar production, and also sparatory. That is the dust will destroy in very hot gas. For example, the supernova shock. And the third one will be the accretion. That is, you can accrete the gas-fed metal. And this process causes the gas depletion in the ISM, the metal depletion in the ISM. And the fourth and third one is, the fourth and the fifth one is the strattering and calculation. Is the result of the grain-grain collision. So, I just briefly mentioned about some environment dependence. So for the accretion and calculation, it often occurs in a dense medium. And for the strattering, it prefers to occur in the diffuse ISM. And for the other two, there is not very significant dependence on the environment density. And for one thing to notice is that the accretion and calculation is the process that will bring small grain into larger grain. And the strattering and sparatory will broken the large grain into smaller grains. And then for the stellar production, it will just, this is the process that when AGB star or supernova, when they inject metal into the interstellar medium, some of the metal layer will condense into dust. And through this process, they mainly produce very large dust, very large grains. So, for all this process, they all are depend on the feedback, but the sparatory and the stellar production is directly depending on the, especially the stellar feedback, like the chemical feedback from the stars, and also how strong the shock, the adjoint shock will be. They will directly affect our dust evolution model. So I will go into talking on the first result of my research. So I'm going to for the purpose of my research is to understand how grain size distribution evolved in galaxies. And for this talk, I was specifically focusing on the grain size evolution of grain size distribution in Milky Way analogs, the NWA. So what our model can tell? Our model mainly, the advantage of a model is to directly calculate the grain size distribution and the total dust abundance. For the composition, we directly taken it from some cosmological simulation, and in this case, it is illustrious TNG. Yeah. So here we're going to show you like what's my research strategy. So first, I choose. So I select some galaxies. In this case, the Milky Way analogs. from illustrious TNG. I chose the maximum simulation volume, the TNG 300. And I post some selection criteria here. And for the reason why I want to select the MWA, the Milky Way analog or Milky Way-like galaxies, is that because we know more about the Milky Way, we have extinction measurement. So I can compare the result of my model to the observation. So here is the selection criteria I used. I used this paper, the 2015 paper, I obtained a stellar map. I used the stellar mass and the specific star formation rate as the selection criteria to select Milky Way-like galaxies. And in the end, I have 206 galaxies that have similar metallicity and the star formation rate as the Milky Way, as our own Milky Way. So the metallicity plot is on the right, the upper one. This is the metallicity, and the gray vertical line here is the measurement metallicity of our own Milky Way. And the bottom one is the star formation rate, and also again the vertical shaded area is the measurement from our own Milky Way galaxies. Okay, so after I have the sample, I extract the stellar mass, metallicity, star formation rate, gas mass, all this quantity from the illustrious simulation, and then put it into my dust model. So let me briefly talk about some specialty with my model. So my model is a one-zone model. That is, I average out all the information of single galaxies. The advantage of doing this is that I can cut down the computation time significantly. And also, because I'm only interested in the statistic behavior of this galaxy, so using one model is okay. And the second thing I do in my model is I try to include gas accretion and also the gas merger. From the merger tree provided by illustrious TNG. Yeah. So that is what that is different things I can do from the previous study. Previous study only mainly focus on one isolated galaxies. So after I have a dust model, I put it into a model and then get the data and then analysis. So how do I analysis? So as you probably know, that the grain size distribution is not an observable quantity. So what I can do is I calculate the dust. Okay, so I calculate the dust abundance by summing all the dust like under this grain size distribution area, under this area, and get the total dust abundance. This one is measurable. And another thing is I calculate the wavelength dependence extinction curve based on the main theory. Like we calculate the extinction and we calculate the shattering and extinction effect only based on the dust composition and their grain size distribution. Okay. So here I'm going to present my results. So first I will first validate our model with the nearby mission of dust metallicity scaling relation, and then I will show you the evolution of the grain size distribution and the extinction curve. So first is the validation. So on this class, the color dot is our calculation result, and the gray dot here is the measurement from some nearby galaxies. So as you can see, our model roughly cover this range that is consistent with the observation. And as you may notice that there are some galaxies at this region, and although yeah, it seems that it's not consistent with the observation, but it's only a minor fraction of the overall population. So we, in our analysis, we just neglect them. Yeah. So overall, it consists with observation. That is the most important thing. And then is the evolution of grain size distribution. So here I show you the grain size distribution, statistics result of the grain size distribution over these 206 galaxies. The solid line is the median value and with the dispersion. So I only start from the redshift 3. Here the dust is dominated by large grain dust. This is mainly come from the stellar production. So the stellar production will dominate the early time. Yeah. And later, as the time goes on, the small grain will increase due to the accretion, shattering, sputtering, and also calculation effect. It will go on, and you can see this peak at redshift 1, and later it decreases a little bit. So there are two things I want to mention here. First is that our model reproduce our model roughly cover the so-called MRN slope at redshift 0. So this MRN slope is some empirical slope measured in 1977. I would believe this is the significant grain size distribution of our own galaxies. Yeah, so yeah, we will say that roughly cover it with the dispersion. The second thing I have to mention is, like you may already notice, this is the green curve. Actually, they have a small dispersion at redshift 1. And we saw that it's due to the chemical evolution and also the gas content, the gas evolution in the galaxies that reach some kind of equilibrium at redshift roughly equal to 1. So, and after this spatial time, the diversity of the metallicity in galaxies and also the gas content drift the grain size distribution away from the equilibrium. And so at this point, like the most significant difference between redshift 1 and 0 is that this bond is decreasing from redshift 1 to 0. And this is caused by the shattering and calculation effect, and which depends on the ratio of the dense and diffuse ISM. So, yeah, in illustrative entry, actually they do not well resolve the dense ISM. So that probably this offset, probably due to the unresolved things, we cannot make sure about this, or we can test it in some future more high resolution simulation. Yeah. So after we have the grain size distribution, we can calculate the extinction curve. So so this dark blue dot is the measurement from 1992, the Milky Way extinction curve. So as you can see, our model successfully reproduced the bond here, this bond, and roughly our extinction curve roughly cover the Milky Way extinction curve as this long wavelength region. And although our model gives a steeper prediction as the short wavelength region, and that's we are trying to working on it. And so that's my result. And in the end, I will bring you some current challenge of our model and also the dust evolution and simulation things. The first thing I will mention is about the dust geometry that is important on the galaxy FED, and I will show you an example later. The second thing is about the grain size distribution actually will be different in different regions in the galaxies, and I will also show you later. And the third thing is, in our model, we have a very simple model on galaxies. example is that the attenuation curve, extinction curve, actually will depends on how many fraction of the star is covered by the dust. So if you have more dust around the star, you will get more attenuation. But you have less dust, you will get the lower one, the less attenuation one. Yeah, that is the thing we can only do in spatially resolved simulation. And also we have to do this with the help of radiative transfer code. And that is what I can do in my current model. And the second one is, I would like to remind you, is the grain size distribution is actually vary from galaxy, galaxies. Like this is a simulation conducted by Oyama in 2020. He directly implemented the grain size the grain dust evolution code into a hydrodynamical simulation of an isolated galaxies. So in his work, he found that at the inner region, the blue line, the extinction is not like significant as the short wavelength region, but for the outer region, more outer region, the green and the red line, you can see the steeper extinction line here. Yeah, so I haven't checked like how will it be if we sum out all the extinction things to the average all the extinction to one single galaxy. I'm not sure about that, but just remind you that the spatial the grain size distribution will actually different from in different regions in galaxies. Yeah. So to sum up, so for my own research, I implemented the dust post-process model on TNG, and also validated it with the dust metallicity scaling relation. And our model really reproduced the MW extinction curve. And also, I have to remind that the scattering and calculation are important to recover a Milky Way grain size distribution. And also that, and also there are some challenges here, and I would be happy if I can solve it one day. But yeah, currently I can for now. Thank you.
Start questions for you, Joe.
So if I understood correctly, so when you compare this dust size distribution with different redshift, so that basically you are taking different snapshot from this straight TG simulation, and then you do this random model to calculate this dust chemical network to get some equilibrium. So, is that correct?
Yes. So maybe go more precisely, actually I put. Actually, I put initialize. So this is the merger tree of illustrative tree. So I initialize it's the high redshift n. Then initialize the dust size distribution as a high redshift n, and let my dust model evolve through this merger tree. Yeah, and what I show on the grain size distribution figure is the grain size distribution at this main branch.
So
yeah.
basically your model also evolve in time.
Yes.
But you consider maybe the density information from this merger tree.
Yes.
So can the dust also be destroyed?
Yeah.
During this evolution?
Yes. Like sputtering, like in our ring break down the large particle from some size of the particle, it can just totally destroy it. And also our assumption, one of the assumptions is that for any outflow of the galaxy, we simply assume that those dust like going into the CGN will never go back. even though they will actually, in fact, they will come back to a galaxy with the inflow, but the inflow gets it too hot, that will probably destroy most of the dust. Yeah. But that is just our simple assumption of this kinematics.
So, follow-up question. So, what do you use for the initial condition for the dense grain size?
Okay, so initially I just, I think I assume an empty space, and because at the beginning there are no dust presents, so like most of the dust process do not happen. The only things can happen is the stellar dust production. So the empty space will only grow up in the large region and turn and as a function of star formation rate, and also mainly as a function of the star formation rate.
Did you have to assume some microphysics parameters for the coagulation and shattering?
Yes.
And is your result sensitive to this kind of parameters?
Our result, well, it depends on part. The part is there will be okay. So they will change, but the most sensitive thing is how many dense gas is in the galaxies. That contributes the most to our data. So that all the other microphysics does not change a lot, as much as the dense gas fraction.
Any more questions and comments? I got a few. On the decrease of the abundance of the large grain size from redshift 1 to 0, where did it go?
Actually.
Eight.
So I follow the. So there's one.
Because there's no increase in any of the other sides. There's only a decrease.
So I presumably we saw that it just be destroyed or going into the CGN. Because at this moment we also observe the decrease of metallicity in our TNG sample.
From redshift 1 to 0, there's a decrease.
After 1 to 0, there's overall shape of a decreasing.
Metallicity? Oh.
And also the density factor also changes this moment, like it grow up a little bit. So it will. So if we enhance
The metallicity means gas-phase metallicity?
gas-phase metallicity.
That's sort of contrary to the observational evidence, right? Usually it's growing.
Yeah.
So, but you don't see it.
Cold gas phase, right?
Yeah.
This gas. So
The cold gas, right? The metallicity, gas-phase metallicity is from the ionized gas. I guess from.
you're talking about increasing again.
Yeah, the increasing by measurements that was the cathode gas. Okay.
In the simulations, you tend to see that kind of flat line, the low redshift, because you're predominantly increasing relatively low metallicity gas.
So that means
So it is a merger actually affects the result wash.
So I think this part, this decreasing in the redshift 0, we did not see in the previous isolated galaxy simulation. So, but I cannot make sure like which part contributes it. So one thing is the interaction between the galaxy and the CGM, and also the merging may also take part into this.
If you have this history and you deploy time, can you, for example, like the movie, see how it evolved in time, saying that corresponding to some
Yes.
event?
Yeah, that would be
should talk to Ken. How to make beautiful movies.
I think one thing is, like, one thing about the merger like cannot be treated very well in our model is the change of the gas kinematics. That will also change the gas evolution, and that cannot be well treated in our model. So there will also be uncertain things here.
Any other questions? I got another one. On the extinction curve, how does that compare to Calzetti curve? I forgot. Calzetti is flat.
Yes.
So you're saying that high redshift, the extinction curve is more close to Calzetti, even for Milky Way like galaxy?
From our study, no.
No, I mean, what? How, if you plot Calzetti curve, how does it look like? Is it more close to the blue?
Calzetti curve, actually, I didn't plot it before.
Right. Okay.
So because our main result is want to compare, first compare like its low ratio.
Do you remember it? I thought it's flat. It's more
Flat,
close.
yes.
Calzetti curve is a simulation curve. It's not for the entire galaxy. So it doesn't necessarily this dust property because it's intrinsic spectrum over the galaxy.
That's right. It also multiplies E minus V, so it's not extinction curve. It's attenuation.
The relation comes by
Yeah.
Right.
It's a Lyman side.
So
Yes, it is.
It's like we assume it's like a result like if there are stars there and the sunlight penetrates through a dust cloud, and what we'll see that starlight becomes on the wavelength. But for the attenuation curve, the thing's different because you have to consider that there are many stars there, and also the starlight can scatter from the other stars. Yeah, and also many other things.
Yeah, I know.
That's the age or something else.
Okay.
Yeah.
It's flat, right? Yeah.
But there is no, that it doesn't make sense.
Right. It's one is total attenuation, one is extinction curve. Yes, that's the difference. I see. Anything else? Questions, comments? If not, let's thank you, Joe, again. This is the end of the session. Any announcement from LLC? No announcements? I guess I'll see you tomorrow. Let's thank all the speakers for today. And let's have a drink.
Oh.